All right, so for this, having a little introduction to what's called a slope field or a direction field, and as a way of visualizing general solutions as well as specifics or particular solutions for differential equations. Now, slope fields, here's an example of a slope field. Each of these little lines, these little dashes represents the slope at some point. You won't generally be required to graph or make your own slope field, not something definitely this complex, but we're usually asked to understand them, and as well as where these little dashes come from, and that's what this question's about. So I have a differential equation here, y prime equals x over y, and I want to create just the slope field at these 4 points, or I shouldn't say a slope field, just the slopes at these 4 points, just to show we understand what all those dashes mean. And so, for example, this point here in orange, that is at 2, 2. Obviously, 2 is the x, the other 2 is the y. That means if I look at my differential equation at this point, the derivative y prime, or dy dx, at that point is the same as 2 divided by 2, which is 1. So on my slope field at that point at 2, 2, I want to show a small little dash that has a slope of 1. And so I'll grab my little ruler here, and a slope of 1 is pretty nice to draw. There we go. Now I'll just make this a little bit shorter, but actually, no, I won't. I'll just leave it like that. Keep in mind, on a slope field, we generally don't have each little line drawn that long. Like I said, they usually look like this, or like this, or like this, but they're usually drawn with computers as well. I'll just leave it nice and long there. And so I'll do the same thing for the other points. I'll kind of go clockwise here. Look at the point in green, which is at 2, 0. That means at that point, my differential equation, dy dx, because it's just x divided by y, is 2 divided by 0, which is undefined. So how do I draw that? Well, keep in mind an undefined slope is a vertical slope, so I just draw a vertical line at that point. All right, nice and quick. I'll go to blue now. So blue is at -1, 2. So the differential equation at that particular point is -1 over 2, or -1/2. So I'll draw a slope of -1/2. I just realized I'm looking at the point in red, not the point in blue. I'll stick with that. Let's the point in red. And so -1/2 is down 1 over 2. So let's do something like that. So that's the point in red. And now the point in blue, that's at -2, -1. And so same idea. This time my differential equation equals +1/2 at this point. Because the negatives divided by negative, as we know, is a positive. So imagine the process I just went through. Make it blue. Imagine that's something that a computer program can do pretty easily and quickly. And imagine doing it for hundreds of thousands of points. And you create a slope field that looks something like this. And so just keep in mind, again, you would never be asked to draw a complete slope field, but you are expected to understand where all those come from. So that said, let's make sure we also don't forget what we've learned before. So determine the particular solution for the point that relates to -2, -1, the last one I drew. So keep in mind, that means if we know the differential equation goes to the graph of it, if we know it goes through -2, -1, that means we know when x is -2, y is -1. So we have a condition, which means we can find the particular solution like we've done in previous lessons. And so let's get to that. Hopefully this is somewhat routine. So if I look at my differential equation, if I separate the variables, I get y dy on one side and x dx on the other. And I'll save myself the time and start integrating this right now. The antiderivative of each side is the same. It's 1/2 y squared plus some constant equals 1/2 x squared plus some constant. I'll put those together and call that constant 1. I want to solve for y squared, multiply everything by 2. I get y squared equals x squared plus 2c1. Square root both sides. I get y equals plus or minus the square root of x squared plus. And now I'll just replace this with a new constant, just c. All right, now that said, I have that plus or minus there, and my solution should be a function, not this, which is not a function. One value of x, two values comes out. So now I need to think about what I have here. And if I look at my graph, I know when x equals negative 2, y equals negative 1. Which means if I look at my solution here, if I replace x with any number, everything here is going to come out a positive. Yet when x is negative 2, y is negative 1. So I know I'm actually just looking at the negative version of this. So I know I want to pay attention to this, y equals minus x squared plus c. And depending on which particular solution I was looking at, I may want to pay attention to the positive one. So this is what I want to focus on. And now all I have to do is figure out what is that constant. And keep in mind again, when x is negative 2, y is negative 1. So I have negative 1 equals negative the square root of negative 2 squared plus c. And I should now really quickly be able to solve for this. I get positive 1 equals positive root 4 plus c, square both sides. And at this point, it's pretty routine. You should get c equals negative 3. And so my particular solution is y equals negative the square root of x squared plus c. Oh, sorry, plus negative 3. Oh, silly me. There we go. There's my particular solution finished. Keep in mind, depending on which points we're looking at, I may be looking at the positive version of that plus minus radical function. All right, so here's a completed slope field that's somewhat pixelated, but we'll do our best with it. Showing the slope field for the differential equation dy over dx equals 2xy. So first, sketch the solution curve. So I don't have to find the equation, at least yet. Sketch the solution curve that passes to the point 1 comma negative 1. And so first, 1, negative 1 is right here. And so now I want to imagine following these slopes. And for example, if I look at this point and go right, well, if I look at my slopes around here, they're forcing me downwards. So it's almost like a current in a stream. And so I have something like this. If I go the other way, I see this sort of natural curve progressing around here, and then it starts to bring me down over here. And I follow these as best I can. It is a sketch. And there's my sketch. So that is a sketch of the particular solution that goes through 1, negative 1. All right, that said, what's the equation for what I just sketched? I just sketched out a function, so I should be able to find the equation of what I just sketched. And again, this is using what I've learned before. And so while I'm not saying this is easy, this should be somewhat familiar if we have a good basis in the last lesson, because I now know when x is 1, y is negative 1. So let's start by finding my general solution, and let's separate my variables. Divide both sides by y. I get 1 over y on one side, dy equals 2x dx on the other. Did I put the dx up there? I did, good. Integrate both sides. So I have the natural logarithm of the absolute value of y on one side. On the other side, I have 2 times x to the power of 2 divided by 2, so just x squared plus some constant on this side. All right, now here, I gotta be a little more careful with this absolute value, because if I look at my graph, I can just see that all my y values are negative. So I can't assume, I don't know that my y values are positive. In fact, I know they're all negative, which means really that I need to at some point put a negative into here. That said, I don't have to do it right away. First, let me solve, at least get rid of the natural logarithm, raise everything to a power with a base of e. So I've, in this case, e and the natural logarithm cancel out, so I have just the absolute value of y on one side and e to the power of x squared plus c1. Like we've seen many times, this is the same as this, which this e to the power of c1, I'm just going to call a new constant, just all of that c. And since I'm only doing that fairly quickly because I've done it a lot in previous lessons. That's it. If I just look at what I have right here, and maybe I'll write my constant first. I now know that y has to be, y itself may be, my y values will be negative at some point. And so the only way that's going to happen is if my constant is negative. So I'm going to now put a negative right there and get rid of my absolute value. Or alternatively, I could leave that positive and get rid of my absolute value and put a negative in front of the y. So that, for example, when y is -1, negative times a negative is a positive, and therefore the natural logarithm makes sense. But I'll go back. It's all the same thing in the end. I'll go back to this. All right, so now I can put in the particulars of what we're told, which is when x is 1, y is -1. And so in this case, I get -1 equals negative c times e to the power of 1. Which means c, with a quick little bit of algebraic work, must be 1 over e. Which means my general solution, if this here is 1 over e, that means my particular solution here is y equals -1 over e times e to the power of x squared. Now, while that's fine, I notice I have a constant of 1 over e multiplied by a base of e. I can definitely put these together. So while that is fine, I should be able to simplify it using what we know of exponents. And so, for example, 1 over e is the same as e to the -1. So I can write this as y equals -e to the -1 times e to the power of x squared. Multiplying two powers with the same base, we can add those exponents. And so the most conventional way of writing this is y equals -e to the power of x squared, take away 1, all in the exponent. Although keep in mind, everything here is equivalent. And that really should be the easiest part. That's just using exponents that we've learned before. The hardest part is doing the other parts before that. If you have time, I would encourage you to graph this, and you should see something that matches this. Just that one solution, not the whole slope field. All right, last question. Probably the trickiest question, but actually will involve the least amount of work. What I see here is a slope field for this equation here, y prime equals sine of x plus y, as well as the particular solution that goes through 0, 1. Okay, so that's shown. So first, let's sketch the particular solution that goes through 0, 3. So that's kind of similar to before. So 0, 3 is roughly right here. And now I want to kind of trace the path of these currents, essentially. So, I don't know, I'll do my rough little, kind of gets pulled this way and then approaches the same curve here. Over here, it gets pulled down. Whoa, whoa, double whoa. Here we go. Nope, no, here we go. And it then gets pulled here and kind of approaches this same curve this way. All right, so that's my sketch for question 1. And for part 2, now I want to look at these two functions. They both have a local minimum. And it says these local minimums lie on the straight line L1. So let's first look at the graph that was given to us, because that was drawn with a computer. The local minimum seems to be about right here, which notice is when my tangent lines, the slope field, has a horizontal tangent. So similarly, for the graph I just sketched, the local minimum should be where I see a horizontal tangent line, so roughly about right here. And the question is telling us that all of these two local minimums lie on a straight line. So while I could grab my ruler and draw this line, also I hope I realize that the straight line really should go through all the points. I'm going to pick a different color than gray. It's a little tough to see. So all these local minimums the two local minimums I've drawn the line through, as well as all the points the line goes through, should really trace over the points where we have horizontal tangents. And if you look at the line I just drew in purple, they all do go through horizontal tangents. So now, what's the equation of this line? just the line I've drawn. It's a linear function. What's the equation of it? It seems to go through the origin. It has a negative slope, but what's the equation of it? So without just estimating, it seems to have a slope of about -1, but I don't want to estimate. So how can I figure that out? Well, it goes back to what I just mentioned. These have to be all the places where my derivative equals 0, where the slope equals 0. And so my derivative is my differential equation. So this must be all the places where the sine of x plus y equals 0. So I need to think, where does y prime or the sine of x plus y equals 0? I can't solve this graphically or algebraically because it's one equation with two unknowns, but I can think about, where does sine equal 0? Well, the sine of 0 equals 0. And so I know that one possibility must be where x plus y equals 0. Because if x plus y together are 0, we got 0, and the sine of 0 is 0. And I've sure said the number 0 a lot, so I'm just going to solve for y, subtract x from both sides. I get y equals -x. And then just double check that this does match up with the line. I say double check because the sine of 0 is not the only place that equals 0. And someone's calling me right now. Toll-free service. I'm not going to answer that. So there are other places where sine equals 0 besides 0. So that's why I got to check and make sure this matches up with what I've drawn, and it does. Y equals -x has a y-intercept of 0. That seems to be what I've drawn. A slope of -1 is what it looked like. So yeah, I'm correct. Good for me. So now the last part is similar, which is, let's look at the local maximums. So if I look at the graph that was drawn for me, it's right around here. And again, it's where my slope fields should have horizontal tangents. And the one in red, roughly about here. So I'll draw this by connecting the dots, and also pay attention to all the places where my horizontal tangents seem to be, or my tangents all seem to be horizontal. Something like, I don't know, something like this. That's it. It didn't actually ask me to sketch it, but obviously a sketch is helpful. So I have another linear function that also goes through all the places where my derivative is 0, but it's clearly not the same line I just drew before. And this all goes back to the fact that right here, when I said x plus y equals 0, that's because I know the sine of 0 is 0, but also there's other places. So just take note that the sine of theta equals 0 when theta equals 0, or pi, or 2 pi, or 3 pi, and on and on and on, in both directions actually. And so we've already seen that when we're looking at where x plus y equals 0, we have a solution that I drew in purple. Let's see what happens if we look at the next one. So let's make sine of x plus y, let's make x plus y equal pi. Because again, there's an infinite number of places that sine equals 0. This time, nice and quick, subtract x from both sides. Y equals pi minus x, or -x. That's a weird looking x. -x plus pi. And then just double check. And yeah, what I see here, it has the same slope as before, but now it has a y-intercept of pi. Ooh. There we take 3, there we go. And then if I look at my graph, yeah, it does seem to cross just past 3. So again, it was a sketch. And so that must be correct. That must be the straight line we're trying to find there. Keep in mind, if I were to find where x plus y equals 2 pi, I would find another solution line up here somewhere, another place for different solutions. And I get a sense that this graph is going to keep repeating, which I can also see down here. For example, I would have another one down here, that would be where x plus y equals negative pi. But I've done more than enough. Notice, I think this is all very abstract work, but of all the questions, this was the trickiest or the most abstract with how to get started, but also had the least amount of algebraic work.